using isosceles and equilateral triangles. We've talked about these some, but we haven't done much for math with them. So today, our goal, at the end of us, you should be able to say, I can explain the base angle theorem for isosceles triangles, as well as I can prove the base angle theorem for isosceles triangles. So you can explain it, you can prove it, and we're going to take a look at that right now. So on your paper, you see this triangle? We need to label it with these different terms. We have base, we have leg, vertex angle, and base angle. The base of the triangle is right here. Okay? And you have two legs. The two legs of the triangle, of the isosceles triangle, the two legs are congruent to each other. So that leg and that leg are congruent. We have an angle called the vertex angle, which is here. This is our vertex angle. And then we have really two base angles. So this angle right here and this angle right here, they're both congruent, and those are both called your base angles. So those are the parts of your triangle. However, if I take all of this information and group it together, you look at this triangle and you're like, oh, the base is at the bottom. That makes sense, right? What happens if I take this triangle, though, and I turn it this way? This right here is still considered my base, even though I turned it. So the base is not the two sides that are the same to each other. It's like the third side. So I have these two congruent legs. My base is that third one that's a different length. Does that make sense? On your paper, you see these different theorems. You need to be able to look at these and understand kind of what's going on here. The base angle theorem says if two sides of a triangle are congruent, so two sides of a triangle are congruent, it's isosceles. Two sides are congruent, then angles opposite of them are congruent. So I have this side, and what's the angle opposite? C. I have this side, the angle opposite, and this angle down here, and that's congruent. Two angles are congruent that are opposite of those two sides. So what do we have? Angle B is congruent to angle C. The converse of the base angle theorem, which says the two angles of a triangle are congruent, then the sides opposite of them are congruent. So now I'm starting here. I'm like, well, hey, if this angle and this angle are congruent, the sides opposite them are the same two congruent angles. So when I look at this, my first question is, well, where's the base at? What two letters make the base? FE, right? Because it's not necessarily the side it's like sitting on. It's the side that's different. These are the same. This one's different. If I said, hey, that is my base. So my equal angles are where? I have these two angles are congruent on my paper, on your paper, right? Angle F is congruent to angle E. Right, because they're opposite of those congruent sides. That's my congruent, so I want to know what's opposite of that angle there. HG and HK are congruent. So I mark my sides, and I am concerned right now just with this triangle with those two congruent sides. Ignore the rest of it that's there. Just look at the blue right now. So if I have that, I'm like, well, where's my base? Raise your hand and tell me where's the base. What two letters make the base? Matt? GK. This right here is my base. So what are my two angles that are congruent? Matt? G and K, and here's where I'm going to be a little picky on you. I know what you're talking about when you say G and K, just because we're talking about this right now. But to name angle K, there's a couple angles here, right? You've got this angle off to the right, and then you've got that whole, like, basically straight angle there. So when you name it, yes, name it H, K, G. When there's multiple angles, you have to use all three letters. So we have angle H, K, G, and then you also have just angle G. We can name that other one just angle G because there's only one angle there. Remember that from chapter 1? The next question. If angle KHJ is congruent to angle KJH, then I'm looking, well, what else is congruent? So here's where I'm going to come in here and I'm going to erase all of this. And I'm going to go back and mark what I have. KHJ, K to H to J, I'm talking about this angle in here. And KJH, K to J to H, I'm talking about this angle. So do you see this triangle? It's kind of like, in a sense, standing on its head, right? Can we maybe take it and flip it around so that it looks right to us? I've got my base angles here. K is up here at the top, and if I'm just flipping it up, I have J and I have H. I have those two angles are marked congruent, so I look at this and I'm like, well, what sides are congruent? Raise your hand and tell me what sides are congruent. Raise your hand and tell me what sides are congruent.
Why did you say angle HK?
Why? Hold on. I'm talking about this right now. What two sides are congruent here? I know Matt knows. Delvian? KH, this side, and KJ, those are congruent. So we have KH is congruent to KJ. Corollary to the base angles theorem, here's where we switch gears a little bit. You look at this triangle and you're like, oh, hey, Miss Rupe, I know what that is. That is equiangular and equilateral, right? So if you want on your paper, you can draw a line right through there. Right through the middle of your paper, because now we're switching gears, and these below are now talking about equiangular, equilateral. The top half we're talking about isosceles. When I look here, corollary to the base angles theorem, it says if a triangle is equilateral, what's equilateral? What'd you say, Heather? All sides are equal? If all the sides are equal, then it's equiangular. All the angles are equal. And the corollary to the converse of the base angles theorem says this. If a triangle is equiangular, then it's equilateral. It just takes those two and it flips it. So really, what does this mean? How does this work? Copy and complete the statement. We're just going to complete the statement. It says if FH is congruent to FJ, if FH is right here, is congruent to FJ, then what angles are congruent? So I'm going to ignore this black line in here, and I'm really looking at this red triangle, right? So if I have two sides that are congruent, what kind of triangle is that? Two sides are congruent. It is, oh, well, you guys know. Two sides are congruent. It's isosceles, right? It's an isosceles triangle. So if those two sides are congruent, we think of this other side then as being the base. So what angles are congruent? H and J, right? Do I have to be more specific with how I name angle H and angle J? There's only one angle here. There's only one angle here. So yeah, I can just say angle H is congruent to angle J and stop right there. Right? Down here, if triangle FGK is equiangular, so I'm going to erase all this. What am I talking about? FGK. FGK. So I'm just concerned with this triangle right here. If it's equiangular, mark it. What's equiangular look like? All three angles are the same measurement. And if FG is 15, FG is 15, we want to find out, well, how big is GK? Why? So if it's equiangular, it's also equilateral. So if this is 15, that's 15. How big is this one? 15. Oh, look at that. GK is 15. Find ST in the triangle at the right. I look at this picture and right away and I'm like, oh, what kind of triangle is it? Equiangular, so that means it's equilateral. So if this is 5, this side's 5, and ST is also 5. So ST equals 5. Notice I didn't put the line above ST because it's equals. If it's equals, I'm talking about that segment length, and I don't need the congruent or the line segment symbol above it. Number 4, is it possible for an equilateral triangle to have an angle measure other than 60 degrees? If it's equilateral, it is also equilateral. It's also equiangular. So is it possible to have an angle measure other than 60? No, why not? Exactly. Every triangle has 180 degrees. If we divide that into 3 equal parts, because it's equiangular and equilateral, every single time it's going to be 60 degrees. So is it possible for an equilateral triangle to have an angle measure other than 60 degrees? No. Every equilateral triangle will always have 3 60-degree angles. Every triangle will always have 3 60-degree angles. Got it? Find x and y. So I look at this and I'm like, well, here's x, right? It's x plus 1. Do I know what that side matches up to? Really, it's the same as this one, right? Because I look at this and I'm like, oh, that's isosceles. Do you see that it's isosceles when I look just at this half of the triangle? Isosceles? Good. Okay. So if that's isosceles, I look and I'm like, well, I don't know what's on this one either. So I come over here and I'm like, well, maybe let's try and look for y first. I look at this triangle, and in this triangle, what is this triangle? What's 4? Y is 4. So if it's equiangular like we see, that means it's also equilateral. So we have 4, we have 4. How big is this one? 4. Okay? Fill in everything you know. Got 4, 4, and 4. So now how about this? Now do I know how to solve for x? Those two sides are equal, aren't they? They're congruent. So say if this was 4, this side is also going to be 4. So x plus 1 equals 4, subtract your 1. So x equals 3. Very good. Check it. If I plug in 3 here, 3 plus 1 give me 4. Yes, does. Got it? Makes sense? In exercises 1 through 4, use the diagram, complete the statement, tell what theorem or corollary you use. So here's where you have to have your notes handy. Don't put those notes away. Number 1, if AE is congruent to CE, here's AE, here's CE. Do you see what triangle we're working with? There's a lot of different triangles there. We've got AE, we've got CE. Connect it. I'm looking at this triangle in the red and I'm ignoring the rest of it right now. What kind of triangle is that? That's isosceles. It's isosceles. So I'm looking at one of the top 2 theorems. These are isosceles theorems. These 2 theorems down here deal with equilateral and equiangular. So based on what I've marked already, does it look like the top theorem or the bottom theorem for isosceles? Top. Piece of cake, right? Yeah. So what theorem is it?
It's 4.7.
The base angles theorem? Okay, I like where Isaiah's going with that. Let's put theorem 4.7. Put the number, that'd be great. Yeah, it is. Been writing it all out. Okay, so I have my sides are marked congruent. I identify my theorem. What angles are congruent? Isaiah? Angle A and angle C are congruent, but we need to be careful because when you look at that picture, there's multiple angles at angle A. Angle EAC and angle ECA. I like it. Angle EAC and angle ECA. Those are my 2 angles that are congruent. I come over here and I'm like, well, let me erase so I know what I'm talking about. Number 2, if angle DAE is congruent to angle DEA, DAE, I'm talking about this angle, and DEA, I'm talking about that angle, so we're talking about that triangle in there, right? It's this angle and this angle. What kind of triangle is that? It's isosceles. So, turn it on. If it's isosceles, we know, well, these top 2 theorems deal with isosceles. Does it look like the first one or the second one? The second one. So what theorem is it?
4.8.
Theorem 4.8. Well, it says tell what theorem you used. So yeah. So if these are my 2 congruent angles, we do have side DE and we do have side DA are congruent. So DA and DE, those are the congruent sides. I put the line segment symbol above them because I'm talking about the segments. I'm not talking about their lengths. Number 3, we erase. We have angle BDF and we have angle DBF. Oh, and we have angle BFD. If you see 3 parts, what are you thinking right now? It's probably going to be equiangular, right? So look at your picture and mark what you have. BDF, B to D to F. We have that angle. We have DBF, DBF is that angle, and BFD, BFD. Oh, yeah. It's equiangular, so it's equilateral, but hold on a second. We need to identify our theorem or corollary down here, right? So now we're switching gears. Now we're talking about equilateral and equiangular. The corollary to the base angle says if a triangle is equilateral, is that where I'm starting?
No,
It's the second one. I'm saying if a triangle is equiangular, then it's equilateral. So this one, yeah, we have the corollary to CCBAT. Okay. Corollary to the converse of base angles theorem. Yeah, something like that. Abbreviate it. I have to know what theorem you're talking about somehow. I guess if you abbreviate it, you got to make sure you get 2 C's in there. Otherwise, it's the first one. So I have my angles marked. I guess. C squared. BAT. I don't care. Number 3. So what segments are congruent if I'm just looking at this blue triangle? BF, DF, and BD. BF, FD, BD. Your 3 sides. So now I come in here and I erase again. And I'm like, well, what do we have? AB. So we're talking about sides now. AB, we have BC, and we have AC. Those 3 parts, it's like, yeah, that's most likely going to be equilateral. So it's the first one. The first one says if a triangle is equilateral, then it's equiangular. So if you say corollary to the base angles theorem, CBAT, I feel like we're in nursing school or something, CBAT. I don't know. So I'm looking at the green triangle. I need to know now, well, what angles are congruent? Can I just say angle B on that one?
No.
Can we just say angle B?
No.
There's only one angle there, right? But when I talk about angle C, there's multiple angles here. So to name angle A, shh. Question? Okay, so be quiet. So I have angle DAC. Or some people may have said, well, hey, Ms. Rube, how about angle BAC?
Oh.
Either way, they're both the same. Not BAE, because I want this whole thing. So either DAC or BAC. And with this one over here, we want this whole thing. So you have angle F, angle FCA, or you have angle BCA. Either way, you need one of those, and you need angle B. I'm going to have you guys get started on this and see how you come on your own. And then when we need to talk, we'll stop and talk and kind of catch up. Make sense? Fair enough?